questions? I'll go ahead and start. Just interrupt if you have questions. So here we got, actually, let me get rid of this. Hide floating meeting interrupts. There we go. Here we have an airplane with single wings, airplane, and then an airplane with two wings, an airplane, and then an airplane with three wings, airplane. So it's like an alkane. So today we'll probably finish chapter 2. We'll see. I think I'll finish chapter 2 so we can start chapter 3. And chapter 3 will be more about alkanes, some reactions of alkanes. And again, it's good to go through these to keep up with the class. Okay, exam 1 grading. So I finished grading the Monday, Wednesday lab students exams, so I can give those back today. And the Tuesday, Thursday labs, I've graded about half of those, and I'll finish those tonight. So they'll be ready to go back for the Tuesday, Thursday people on Tuesday. And then the exam average so far, it's not 68, 69% so far, which is low. I like it higher than that. It is the first exam, and we are in a pandemic, but I want us to do better. When I was grading it, it felt worse than that. I was like, wow, this is one of the worst exams I've graded. And I was trying to think of why. I'm like, am I just not knowing how to teach anymore? Or I don't know what's going on. But then I do notice like I don't get many people in office hours. And I don't have as many students like hitting me up for like the exit question checks and answers and things like that. So yeah, I think we can do better. I have one theory. Maybe it's because students are used to taking exams online when they can have full resources. So they get this feeling of like, I kind of understand the material. And when I start the exam, I'll find the answers and I'll kind of get it done during the exam. But from now with my exams, you have to like not just kind of understand it, you have to know it and you have to be able to do it. So you have to practice doing it. So we'll get there. Yeah, I like my averages in the 80s, not the 70s. So we had a high of 92, and we got more exams coming Tuesday, Thursday. I don't know if that's going to lower this exam average or not. We'll see. Hopefully not. Okay. Who asked for the transcripts? Because I like the transcripts, but I don't know how to do it myself. So whoever asked for it just now, let me know some point how you requested it, because maybe I can figure out how to do it too. Here's a more. Oh, I found it. More live transcripts. Okay, I'm good. I know how to do it now. Yeah, I can do that each time. If you like that, remind me. Okay, so to get full points, oh wait, I'm sorry, I didn't say what this is here. So I do something called exam corrections. I feel like it's one of the best tools I have of learning, because the material that's from exam 1 is also going to be in exam 2 and exam 3 for the final. So if you don't learn it from exam 1, then you're just going to be in trouble for 2 and 3 because it builds. So when I first started teaching, I thought, oh, I don't want them to like miss something on exam 1. And then again, that material hurts them on exam 2, keep hurting them. I want you to really master the exam 1 material, even if you didn't have it mastered during taking the exam 1. So I thought, oh, I'll have them do corrections, and I'd have them like, just go to the answer key and correct all the wrong answers. And then I thought later, I'm like, oh no, I'm going to add sentences. So to get full points for this assignment, you're going to correct all the errors you've made, and even errors that didn't take points away. Like sometimes it's like a really minor thing and I comment on it, but I don't take a point. But then still correct that. So that means like writing out the problem. Don't just like, some students get really lazy with it. And I don't want that. I want you to like, rewrite it, because apparently you didn't know the first time. Let's get you good at it. And even more, I want you to write sentences, or sometimes a sentence will do, but about each question you got wrong, why you got it wrong. So I think when you take time to formulate and try to figure out where you went wrong, you get a lot out of that. And then you know this material much better. So then when next exam comes, you do better. Don't write sentences like, oh, I just brain farted this one, or I didn't study this. That's kind of like a lazy answer. I want you to give a meaningful, thoughtful answer, like something like this. Let's say you say you missed the transition state diagram. or drawing a transition state on the reaction coordinate diagram, and you say something like, it does not make sense to draw a lone pair of electrons in the transition state when they are represented in the dotted bond that is breaking. So that sentence doesn't make sense. I probably should have showed this first. So let's look at this question from this. This is a step 2 of the mechanism from question 8, where the water molecule is leaving. And so this red pair of electrons is becoming a lone pair on the oxygen of the water. It wasn't a lone pair at the start, and it's not a lone pair in the middle. It's a lone pair, a red lone pair at the end of the products. So when you draw the transition state, it wouldn't make sense to have a lone pair here on the oxygen in the transition state, because this pair of electrons in the red bond are breaking in the transition state. They're not a lone pair yet. They're not a lone pair until the reaction's over. So this wouldn't be correct, but this is correct, where now you just have the lone pair that was there all along. You don't have an extra lone pair on there. So I want you to really think about it and understand it that deeply. And so when you have errors throughout your exam, just make good comments and we'll get good at it. Now use the exam key for these corrections too. I don't know if some people get confused or they're just like not putting effort into it, but I'll see a lot of times it'll be a corrected answer and it'll be completely wrong again. I'm like, wait, you have the answer key. So you're supposed to look at the answer key and write out your correct answer perfectly. So let's do that. And then after exam 1 quiz. So I started doing these corrections and I thought it helped, but then I noticed some of the students would just blindly kind of write out the correct answer or just kind of almost mindlessly be copying it. And their sentences, maybe it would help a little bit, but they still didn't really learn it. So then I thought, oh, I'll give a quiz after the exam because, you know, I like to give more quizzes and have more grading for me to do. And then I have to enter it and then give it back. Just make more and more work for myself. Just kidding. I do it for you. So what I do is for this quiz, this after exam quiz, I say you're going to get a problem from the exam and it's going to be randomly given out to you. I just print up like each question of the exam and I just go to the first person, they get question 3 and then it goes 4, 5, 6 down the line. So each of you will get one of the questions from the exam and it's going to be, it could be from either version. I actually had 2 versions of the exam. So, but the questions were similar. So, but check on both versions. Check out both questions on the key. They're both on the exam key. So I could give you, you know, the spectroscopy one or this reaction coordinate diagram one, whichever one I give you, you're going to get that one and you're going to do that problem. Like when you did it on the exam, no help, you know, whatever. And then so what you want to do is study the exam key and practice it so that you get good at those ones, especially the ones you missed. But not only that, the ones you got right. Sometimes you get one right and you don't really look at it much. And I don't know, you just already forgot, which isn't great. And then you go to the quiz and you miss it. I have that often happen where a student got a question perfect on the exam and then on the after exam quiz, they got the same question and they missed it. So don't do that. All right, so I'm trying to really make sure this exam 1's not like something like, oh, we're done with it, let's put it behind us. No, we're gonna get this material. We're not done learning. Okay, and I want you to also look back on exam 1 and like say like 4 or 5 weeks, you should look back on exam 1 and be like, oh, that was so easy. How did I miss that stuff? Because you've gotten so much better at this. Okay, for students with testing accommodations. So on Thursday, I didn't get to the testing center by 3. It was like 5 o'clock when I still had students in lab and I was like, I guess I can't get it till, no, not Monday, not Tuesday. I can't get your exam till Wednesday at 9 a.m. So I will, for those of you who took the test in the testing center, I will grab it on Wednesday morning and grade it quickly and I can have it. You can come by Wednesday if you're in a Tuesday, Thursday lab section to grab it, or Thursday, I'll hand it to you. And then since you're not getting it till then, I'll have your after exam quiz and corrections due the following week on Monday, Wednesday. Okay, and then join the Chem Club. You can get +1 extra credit point for it. Here's a little info about it, and they emailed me a video. So check this out. This is pretty good. I'll turn up the volume for you.
Welcome to the Chemistry Club. My name is Dalmanpreet and I am your president.
I'm Kimmy and I'm your vice president.
I'm Stephanie and I'm your secretary.
My name is Saibpreet and I'm your treasurer.
We are thrilled to announce that the Chemistry Club is back.
Join us for tutoring and gain access to opportunities to broaden your chemistry or STEM knowledge.
We meet every Friday from 3 to 4 p.m. over Zoom.
And for further information, please join the Chemistry Club Discord, which will be linked at the end of the video. Thank you.
God,
I just ruined my moment, Kimmy.
Thank
Sorry.
you. Oh snap!
You just ruined
I
the
read
thing.
the previous.
Okay,
It should be part of the bloopers area.
All right, so I really recommend you join the Chem Club. Not that it's like, oh, you need to join clubs, but you'll get extra credit for it. But also, like 2 of the students in this video were like superstar students of mine in the past. So when you go there, you can get help too. If you're like working on a homework problem, you're like, I don't get this. They're the ones to go to. And so, yeah, I think some of you are going to not be happy with your exam 1 score, but it's the start of the semester. Let's get rolling. Come to my office hours if you can. Go to the past peer sessions. You're really lucky to have a past peer and Chem Club. You can get help there too. There's lots of places to get help. Take advantage of them. And then work on campus. I saw this up on the wall outside of my office, and I think it's a great idea if you can get a job on campus. I remember I used to work at a grocery store for a while, and then I got a job at my school. And when I got the job at school, it really helped because I didn't have to drive off campus to my job. I just, I would have like my class, and then my job started in 2 hours. So I was like, oh, I'll just stay here and study. And it just sort of keeps you around more, and it helps a lot, I think, because once I left campus, I would still study at home and everything, but it was like more distractions, more going on. All right, so you can come use the NMR, like I've said before, during office hours and before my first lab section. So like Monday, Wednesday from like 1:30 to 2, today 1:30, come on by. And then Tuesday, Thursdays 9 to 10:45, like at time you can come on in. If you do come in, you can do NMR IR, but you can also do the experiments, the solubility of organic compounds. You can do that too, but don't be doing it up to the lab period start time. So the lab starts at 2 p.m. I don't want you to have all your stuff out, so that they got to come in and put their goggles on. Just end a little early, but you can be on the NMR. All right, for those of you who come to my office hours, get extra credit. So let me know if you did that so I can give you the extra credit. And experiment updates, we're still working on the NMR. Some people have already gotten their all their NMRs done, the ethyl acetate toluene and the unknown. So we'll keep making progress on that. That'll be happening in the background of other experiments. And then I've said before, I really want you to get going on the solubility of organic compounds. If you're not through 14 by today and tomorrow, then you have to lose some points, 5 points from that assignment. So that should have been done like not last week, the week before. And then also I'll have you take a quiz today and tomorrow on part D of this experiment, solubility of organic compounds. The material is here, and there it is. It's got the actual quiz in there. Another experiment update. I finished updating the crystallization of organic compounds. That's our next experiment that we're going to do. And spend at least 1 hour working through this assignment as it's pre-lab, and tell me how far you got on this Wednesday and Thursday of this week. So the pre-lab for this is due Wednesday, Thursday, and what that is you just start doing the assignment for an hour. I don't think in an hour you'll get to the point where you need to do lab work yet. But if you do get to the point where you need to do lab work in an hour, then just say, oh, I got that far. You don't have to go a full hour. And I want to encourage you to do this because I felt like we're like kind of behind in lab right now. So I want us to get moving. So I'll make this as a 5-point deduction from the final grade of this assignment if you don't have at least done an hour. So what does that mean? You can't say, oh, I just did 1 page. It took me an hour to get to that 1 page. Now you got to get more than 1 page. And I want to see how far you get and average it. So then maybe next year I can say, oh, make sure you get to page whatever as a pre-lab. And then the schedule. So I've added this stuff to the schedule. So today we have the quiz, Big 4 acid and base reaction solubilities quiz. And that's today and tomorrow, Monday, Tuesday. Wednesday, Thursday lab periods, you have the crystallization. Start doing the crystallization, spend an hour on it. Show me how far you got. And you also have, that's a busy day. We got a pre-lab, we got the exam 1 corrections and the after exam quiz. So do that for this week. Let's see, did I miss anything? No. So homework B is posted. Start working on that. We're almost done with chapter 2. So that'll have a due date soon. And there's the problems from chapter 2 are in here. They're a little bit, you got to fish a little bit, but you can find them. And then also just ask me in office hours, things like that, if you have questions. Feel free to come to lab early, like I said. Does anyone want to come today? After lecture today? Run the NMR, do some solubility of organic compound. Anybody free to come today? Well, if you are, come on in. Okay, and then check your Sierra College email for me. Sometimes I feel like I send out an email that's important, and if then the student doesn't see it for a week. So I think you need to be keeping up on that. I feel like the Sierra College email is maybe gets the slowest response from everyone. I think the announcements done in Canvas get the best reception, but I want you to still know that. Check your email. And I sent an email to honor students who could not make the meeting. So check that one out if you didn't make the meeting on Friday, the honors student meeting. And I noticed, I'm really glad that we're back in lab in person, but since we're not in lecture in person, there seems to be a delay that's hurting people. So I noticed some people, a number of people on the exam one, they hadn't watched Monday's lecture fully. So when they got to that question about nomenclature, they're like, I've never heard of this. I'm like, oh no. So I encourage you to come to lab live if you can. I mean, to lecture live if you can. But if you can't come to lecture live, you should try to watch that lecture the day of, because it's got a lot of timely things to get you going for that day. And all the other thing that's really hurting, it feels like I give like an entrance question in the Monday, Wednesday labs, and many of those students couldn't attend the lecture. So they're kind of like not getting as much out of it as it could. It's just, this pandemic sucks. I want it to be over. And then now we have an SOTW. She went to Horizon Charter School in Auburn area. Did junior and senior year at Sierra College, junior and senior year of high school at Sierra College. Chemistry major. Will become a veterinarian. Oh, I don't know why that came up twice. Has ridden horses since the age of 4. Current horse is Buzz. Has 3 snakes, 4 tarantulas, and a dog. The snakes are Menchi, Nagini, Opie, and the spiders are Octimus Prime, Pluto, Quadarius, and Rapture, and the dog Saber, and has been to every continent, including Antarctica. That's pretty cool, huh? Not many people have been to Antarctica. And here she is, Alex Dutcher, kind of like Butcher, but Dutcher. And here's, I don't know if this is Nagini. I'm not sure. I don't know. I forgot to ask if she can speak parcel tongue. I think I did. Maybe I did. But I don't know if I can understand her answer. So she is with her older dog, Bowden. And this is Buzz, her current horse, and there's Buzz's mama. And, oh, where did I go? And here's Saber, her current dog, Saber. So let's give a round of applause for our new student of the week, Alex Dutcher. Okay. So any questions about the outline so far? Okay, so let's start lecture. So we are talking about acid and base strength. So we looked at atomic size and used that to predict base strength, which then we used to predict acid strength. Let's actually take a quick glance at that to kind of review and set us up. So that was the lecture on Wednesday. Okay, we looked at things like this one. So when I look at this ethanol and the thiol here, Which is a stronger acid? Well, I'm going to make their conjugate bases using water, the most common solvent base to use in this type of thing. And then I look at the conjugate bases, and whichever base is more stable, whichever base has got the negative charge lower in energy, that's going to be the weaker base. And once I figure out the weaker base, then I can say its conjugate acid is stronger. So which is the stronger, which is the weaker base? So I've got sulfide here. It's got a negative charge on a less electronegative sulfur. Oxygen's got the negative charge on the more electronegative sulfur. But the sulfur is a much bigger atom, so that negative charge is spread over a bigger area, and that size dominates the electronegativity. So this is a weaker base, and thus a stronger acid for the sulfide. And I think, did I have some pKa's for that one? Yeah, I talked about the sulfur being bigger. Its radii is 103 picometers versus oxygen's only 73. And then we did a similar thing with the hydrofluoric acid and hydrobromic acid. Hydrobromic acid stronger because its conjugate base is more stable and weaker. Its negative charge is spread over a larger area. And then when we looked across, when we look down a periodic table, size increases greatly. Across, it only increases slightly. So across a period, this is down again, huh? Across the periodic table, yeah. So sulfur, phosphorus. So sulfur and phosphorus about the same size. Let's go check. Sulfur 103, 110. Yeah, not that big a difference between sulfur and phosphorus in terms of size. So when there's not that big a difference in terms of size, then it's about electronegativity. So sulfur is closer to fluorine. It's more electronegative, so it can handle the negative charge better. It's a weaker base. Thus, its acid, conjugate acid is stronger. And I got a pK of like 7 for the hydrogen sulfide, or hydrogen sulfide, yeah. And I got a pKa of 27 for this one. Okay, so now we're going on to over here to the right. Atomic size. Now let's look into resonance, and then we addressed electronegativity already, actually. I should change the wording around. I like doing it the way I did it this time better. And okay. So resonance. What is resonance? Resonance is it describes the flow of electrons pi bonding. And resonance can help stabilize negative charge and positive charge. They can spread out and stabilize. And positive charge. So you see how we're going to use this resonance in this case, because conjugate bases will usually have negative charge. So we can, if resonance can help spread out the conjugate base's negative charge, make it more stable, make it a weaker base. So let's look at an example. So you can tell me right away, I think, which is the stronger acid here. But we're going to then try to confirm that with this idea of resonance. So if I compare these two, oops. I'm going to have water deprotonate both. Which of these two is the stronger acid? type in the chat. Oh, boy, I got some email. Yes, Santos got it. Santos just told me that what did I do? I drew two carboxylic acids. I wanted just one. I wanted one to be an alcohol like this. There we go. There we go. Okay. So the carboxylic acid's pKa is about 5. So it is more acidic than the alcohol below with a pKa of about 16. As I promised, we'll keep talking about these pKas. Should have them ingrained in your brain. All right, so when I look at these, I see this conjugate base has all the full full negative charge on the one oxygen. Okay. Whereas up here, this has resonance. Lone pair can come down like this, and pi bond could swing up like that. So that negative charge is spread over two oxygens. So that makes, what would that do to the carbox? What would that do to, this is a carboxylate. So the carboxylate has the negative charge spread over two oxygens. So does that make that carboxylate a weaker base or a stronger base? So if you spread the negative charge out, it's not so concentrated. It's a weaker base. It's a weaker base than this. So let me make sure we got a weaker base, stronger base. Okay, so I saw a lot of wrong answers on the chat. Does it starting to make sense? Like, oh, this negative charge is on one atom. It's really hot. It's got concentrated. It's ready to react. Where this one, the negative charge, oh, it's kind of mellowed out. It's spread over the two oxygens. And we can draw the resonance hybrid to help us see that too. So the hybrid, remember, it would look like this. I think one of the reasons why when I was grading the exam, I was disappointed was the resonance structure question. That's like full on just general chem. We did not do well. I was like, oh my goodness, this is not good. We'll get there though. Because I spent like seriously 25, 30 hours on making that, how to do resonance structures GSA. And then the question was like, wow, it's like as if they've never seen, a lot of students, as if they've never seen resonance structures and Lewis structures. Oh. So here we go. My negative a half is terrible. It should be negative 1/2 each oxygen, right? So that means that wouldn't it be stronger to base with a full negative charge, which is only half a negative charge? So yeah, this is a weaker base. And since it's a weaker base, the weaker base will have a stronger conjugate acid. Okay. Yep, Alina, the conjugate base, if it's stabilized with resonance, that makes it a weaker base, and then stronger acid. All right, so I do have some practice problems that I haven't if you go to our step-by-step, which I'm showing you now, chapter 2, reactivity. I click on that. I got some notes that I followed along with before, but I didn't want to do it this time. Sometimes these notes, I kind of clipped out some of them. You can check them out. Got some practice problems here. Let's see. I go at the end. Yeah, this one's pretty good. Let's see. Oh, why did it start at the beginning? I'll fly through this. Yeah, this is a good point here. So I think of certain acids as the super duper strong ones, the ones that react completely in water. So all of these, tossic acid, we'll see that later. It's similar to sulfuric acid. And then we have strong acids like hydronium and protonated alcohols. They got negative pKs, but they're closer to 0. And then weak acids like phosphoric acid, acetic acid. And then we got the extremely weak conjugate bases for the super strong acids. Their conjugate bases are super weak. So we're not going to really see them act as bases much. And then the conjugate base of these are they're weak, but not extremely weak. So water will deprotonate things, alcohols will deprotonate things. And then the conjugate bases of these, they're weakish conjugate bases. They actually can have a relative amount of strength. So we'll see them acting as bases a lot. So the pattern is extremely strong acid, the bases are almost not even, their conjugate bases are almost not basic at all. And then when you have weak acids, your conjugate bases can be weak as well. All right, rarely deprotonate strong, super strong, just only, well, yeah, these will deprotonate super strong acids and just strong acids mostly. Yeah, and deprotonates all acids except extremely weak ones. All right, so we got this. Well, actually, this one's pretty good too. Okay, so I did say last time that base strength increases as you go up because the atoms get smaller. So the negative charge they have kind of sticks on them more concentrated, but it gets the base strength gets weaker but stronger this way because they're less electronegative. They can't handle that negative charge so much. So like these are KB values, or I'm sorry, PKB values, like a pKa of an acid. So remember the pKa of an acid, the lower it is, the stronger the acid. So what's the stronger acid? What's the stronger base? PKB 11 or hydroxide at pKb about -2. Who's the stronger base out of these two? Hydroxide or fluoride? What's the stronger base? Okay, our answers are all over the place. Hydroxide is a stronger base because it has a negative pKb. It's got a lower pKb, stronger base. And then, is this a stronger base or a weaker base? This is called amide. Stronger again. It's got even lower pKb, huh? So this one As we're going to the left of the periodic table, we're getting more basic. As we go down, now what's the stronger base? 11 ppb or 21? So the stronger base is fluoride. Fluoride's a stronger base than chloride. And then bromide is, what's bromide? I can't, my thing's in the way. 23, yeah. Didn't change that much, but it did get weaker. So just as we said, we get more basic as we go up because the atoms are getting smaller and they're getting more concentrated negative charge, not spread over as big an area. But as you go left, the atoms get larger, which spreads it out slightly, but not much. It's more about electronegativity then. So the less electronegative you are, the more like you don't want that negative charge, the more reactive, stronger you are. Let's see if I can throw this in the Jamboard. Where was I? Was that in the online PowerPoint? I think I was. There it is. Okay. Okay, let's look at some of these ones. Do like this one. Okay, so which one is the stronger base? I like this one. So let's draw the conjugate base of both. So this one's conjugate base would be a carboxylate. If I added water there. I'm not showing the curved arrow mechanism just to speed up this part. And then this one, if I add water and then deprotonate it. Ooh, so the first thing you have to ask is where will it be deprotonated? Will the nitrogen be deprotonated or the oxygen? What's your guess? So whenever I ask questions like this, like for example, this first one, I didn't tell you, oh, we're going to deprotonate the hydrogen off the oxygen. But I did that. But I mean, I think you would have figured it out as well. But there's also hydrogens on this carbon and this carbon that could have been deprotonated maybe, but they weren't because this one's the most acidic hydrogen on the molecule. This is way more acidic than that. This one's pKa is about 5. This one's actually got a pKa of about 25. And that one would be like 50. So who's more acidic? The nitrogen's oxygen, nitrogen's hydrogen, or the oxygen's hydrogen? Well, there's going to be resonance involved in this as well. But if we didn't even consider resonance, let's compare like ammonia to water. Who's more acidic? So what's the pKa of ammonia? pKa of ammonia is 35, and then water. It's like 16. So water is much more acidic. So your first guess should probably be, oh, it's probably going to be the oxygen gets deprotonated. So yeah, let's try that. Okay. Now, when the oxygen gets deprotonated, is there anything that could stabilize it besides just the oxygen, say electronegativity? Before we answer that, we can look at this guy. Does this one have resonance? It does. Oh, also, when you draw resonance, always do the double-headed arrow between your resonance structures. So this conjugate base has resonance to stabilize it. Oh, what the hell? So this one has resonance to stabilize negative charge. And are the resonance structures, what did I do? Are they the same or different? Are they equivalent? Are they degenerate? So Santos was asking, do we have like 50% of the time it's got the negative on the oxygen up here and 50% of the time? Nope. Resonance is just a tool, and it's just meant to help us understand what the true molecule looks like, which is more like the hybrid. So the hybrid is where you have like you don't have a single bond, then a double bond. It's like you have a 1.5 bond the whole time. 1.5 bond the whole time. So for these ones, the two resonance structures are degenerate, same energy. So then that means your hybrid would be 50-50 mixable. So your hybrid is what? So the reality is it's not switching back and forth. It's like this, -0.5, -0.5. They each have -0.5 because they're equally sharing the negative charge. Okay, so now what about the one up here? Does this one have resonance to stabilize it? It does. Just like that. Okay. So yeah, there is resonance. Are these two resonance structures degenerate? Are they the same energy? Or not degenerate? Which is major then? Which one's the major resonance structure, since they're definitely not degenerate? Is it major, the one with the O minus or the one with the N minus? O minus, this one's major. So that, why is it major? nitrogen and oxygen are about same size. But oxygen more electronegative. Since the oxygen is more electronegative, it can handle the negative charge better. Lower in energy with negative charge. Okay, so that's the major resonance structure. So what's the big deal about it being the major resonance structure? What that means is the molecule will look more like the major resonance structure. Hybrid. Like the major. So let's draw the hybrid. My iPad's behind, sorry. Okay, so here we go. Looks like that. And so there's a -1 charge being shared over both. You know, I'm gonna draw this a little different. Yeah, I'll start fresh. I think I like it better this way. Moving that hydrogen over to the left. Okay, so now there's a -1 charge shared between the oxygen and the nitrogen. Do they share it equally? No, they don't share it equally. So I'm not going to put -1/2 on both of them. Instead, I'm going to put, say, let's put like negative, I don't know the exact value, -1/3 and like -2/3. So there's going to be more negative charge on the oxygen. Okay, so which is the stronger base of these two? So we have this base here with a -2/3 oxygen and -1/3 nitrogen versus this base, which have a -1/2 and -1/2 oxygen. Which is the stronger base? This one's the stronger base. Because when we ask which one's the stronger base, we also ask, which part of the molecule is basic. So on this one, we have the oxygen's basic and the nitrogen's basic, but the oxygen's got more negative charge. I think that's probably more basic. And that if that oxygen we're saying is -2/3, then our oxygen over here is on the acetate or the the carboxylate. It's only -1/2. So -1/2 is lower charge than -2/3. All right, so this is the stronger base, if that, because there's more negative charge concentrated on the oxygen. So if that's the stronger base, then which one of the acids is the stronger acid? That's the stronger acid because this is the weaker base. A lot of strong, weak, back and forth, huh? And then I was going through, I just picked out my favorite example on here, but here's some more practice for you. I'll put this in PowerPoint and then slide. So there was a question on the chat about minus a half, minus 2/3. Okay, so what I'm thinking here is when this base here, when it reacts with an acid, it's going to react either with this oxygen or this oxygen. And when it reacts with either one, it has a negative one half charge. So it's like half a negative charge here. Whereas when this one reacts with an acid, it'll react with the oxygen. It's more negative than the nitrogen. And even though it's more negative, but it does have, it's less electronegative though, huh? Then, I mean, it's more electronegative, so maybe it can handle the negative charge better, but it's got more charge. Let's say this is the more basic atom, the oxygen versus the nitrogen. And also we kind of have to react here because we need to get back to the same conjugate base, this conjugate acid, I mean here. So if it's going to react at this oxygen, that's negative 2/3 versus this oxygen at negative a half. Negative 2/3 is greater than negative a half. If you do like a number line, you have like 0 and you have a half, and then 2/3 is greater. Like a half is like 50% there. 2/3 is 66.666%. So this is more negative. It's a stronger base. If it's a stronger base, then it's going to have a weaker conjugate acid. I mean, a weaker conjugate acid there. Does that help with that? Okay, here we go. So sorry about that. So we have acetic acid here and water, and this is what's called a vanillagous acid in water, but we don't know the pKa of the vanillagous acid, so we can't just by memory of pKa tell which one's the stronger acid. But by analyzing the conjugate base, we can make a good guess. So let's do that. So the acetic acid comes out like this. And does this acetate have resonance, this carboxylate that we just made? Does it have resonance to stabilize the negative charge? Yes. That negative charge is spread over the two atoms. So it stabilizes it some. Now, what about the vanillagous acid? Let's go over here. We got the conjugate base. It has negative charge right there. Does it have resonance to stabilize it? It does. Yes, it does. And oh, here, let me draw the curved arrows. The curved arrows really help you with the resonance, and take the resonance step by step. So I like you to notice this pattern for resonance. You have a lone pair. Lone pair of electrons, and then a single bond. Bond. Then a pi bond, a double bond. So lone pair, single bond, double bond. So what I'm talking about is right here. This oxygen's got a lone pair, then we got a single bond, then we got a double bond. So we can do resonance like this. Okay, so do we have that below? We do. We've got a lone pair. Oops. Lone pair. Single bond. Double bond. So let's have resonance. We can drop this pair of electrons, this lone pair, in to make a pi bond there. And then this one can become a lone pair on the carbon. And see how I did this resonance with just two curved arrows, just taking it step by step. And now this carbon has a lone pair and a negative charge. That carbon has one hydrogen on it. It still has one hydrogen. So its formal charge is, group 4 minus 1, 2, 3 bonds, 4, 5, 4 minus 5, -1. Yep. And we also know that our resonance structures, like if this resonance structure has a negative charge, other ones have to have a negative charge overall too. Okay, so we got that resonance. Is there more resonance? Can we spread this negative charge out even more? Let's see, we do have a lone pair, single bond, double bond. So yeah, we could still have more resonance for this. So this lone pair can drop down like that to make a pi bond, and then this pi bond comes up, becomes a lone pair too. Oh. There we go. So this conjugate base has 3 resonance structures that spread out the negative charge. So let's draw the hybrid. Oh, well, before I do the hybrid, are these all equivalent? Are these degenerate resonance structures? Not degenerate. So which one's major? Or which one's? So what do you think? Is it the O minus that's more major, or having the C minus or the O minus? Yeah, I'm gonna say this one. You're on the right track, Ryan. This one is major. This one is major. And this one is minor. And that's because carbon is less electronegative and can't handle the negative charge as well. Okay, so let's check out the resonance hybrid. Now our pi bonding is spread over all these atoms. There we go. And since the 2 O minuses are major, I have to come up with some fractions that'll add up to 1, but it'll be more on the oxygen. So let's see. If I were to go 1/3, 1/3, and 1/3, that would be if they're degenerate. They're not. So let's go, like maybe if I went 2, 6, 2, 6, no, 2, 6. Let's go. That's probably it. 3/9, 3/9, 3/9. And then I can add 1 to each side. I like that. So I'm going to say this guy is -4/9 on this oxygen, -4/9 on that oxygen, and on the carbon, just -1/9. So that still adds up to 1, but I'm showing that it has more on the 2 major ones and less on the other one. -1/9. Now, I don't know if it's exactly -1/9 and -5/4. I just know it's more on the outer oxygens and less on the carbon. Okay, so which is the, back to our original question. We're trying to see who's the stronger acid. So which one is the weaker base? What's a weaker base? Having this one with the negative charge spread over 3 atoms, or the base where the negative charge is spread over 2 atoms? I guess I didn't draw that. You've seen that hybrid a lot already, huh? This acetate hybrid. They're degenerate, so it's -1/2 on each. What's greater, -1/2 or -4/9? Yeah, so this is funny. We're doing fractions. You would think, okay, there's no math, but so -4.5 over 9 equals -1/2. So -4/9 is less. It's a lower number. Kind of wrote that sloppy. So this oxygen is less negative than this oxygen. So this is a weaker base. And if that's a weaker base, this is a stronger acid. Yeah. And if you look at pKa values for these, what's the pKa of acetic acid? 4.7. That's one you've memorized. The pKa of this guy is about 3. You take the pKa down about 2 units when you have this extra resonance. So when you look up the values, it supports our theory. It's more acidic. Okay. We did it. We're getting there. So we've talked a lot about acids and bases. We predicted them. We've learned they're just to memorize the pKa's. And we also learned when you don't know the pKa's, or even if you do, you can consider the conjugate bases and think about the atomic size that has the negative charge, the electronegativity of the atom, and also if it has resonance to spread out the negative charge. And once you know about the base, that's great. You can say this is a stronger base or weaker base, but you can also then correlate to their acids, like their conjugate acids, predict their strength. What is the name of? I don't, it's a vanillagous acid. I don't know. I got a question about the strength of this, the name of this guy. Let's see. I'll draw it up in Marvin's sketch and ask it. Oxygen here.
Thank you, Dr.
Okay, and then I highlight it and go. Okay, so this one is 3E4 hydroxy but 3-ene-2-one is a ketone and a so this one's a little beyond our naming so far. There you go. The E talks about how around the alkene part, it's not actually an alkene, it's an enol, but the oxygen and the carbon, the ketone are on opposite sides. That's the E part, 3E, and hydroxyl, and the one ketone. All right, so that won't be a nomenclature question on your next exam. So now we will I'll let you look this up, answer 12. I made up this as an outcome because it would bug me. I would give my students the American Chemical Society exam at the end of the year, the ACS exam. Did any of you take the ACS exam for general chem? So the ACS exam, I'm not a huge fan of it because it seems like it just has some random questions. You're like, oh, that's just a factoid type question. And one of them that seemed like it would come up a lot would be like, oh, if you have a branched or cyclic alkane, who's got a higher boiling point? And it's just silly. So I didn't. So I put this in there. So look it up yourself, see what you think, or ask me about it, because I think Newman's are way better. So, but actually, I don't give the ACS exam lately. I didn't give it. I haven't given it since the pandemic. I think I might have given it right up until the pandemic, like my first 15 years of teaching here. But I always felt like weird about it. My students did fine on it. I probably averaged like 80th percentile on the ACS exam, but it would bug me when a student would miss one of these little random factoid questions. But okay, so now on to Newman projections, Newmans. So yeah, we're gonna do the energy versus reaction point diagram. Okay, so what is a Newman projection? So a Newman projection is a way to view down a bond. And then when you look down the bond and make energy versus rotation predictions. Okay, so that's a big sentence. Let's look at an example. Yeah. Let's say we're going to look down this bond right here. We're an eyeball, some eyelashes, and we're going to look down this bond. What bond is that in terms of nomenclature? That's the carbon 3 to 4 bond, because this molecule is 2-methyl pentane. Okay, so we're going to view down carbon, oh, I'm sorry, carbon 4 to 3, huh? Carbon 4 to carbon 3. So let's draw it again, but with the hydrogens shown on carbon 3 and 4. And I'm going to make them colorful too. Let's go like blue for this one, green for this one. And yellow and red. Okay, so my eyeball is looking down this bond. And when I draw the Newman projection, there's rules you have. What you do is you draw the first carbon you run into, you draw that as a little dot. So that's carbon 4 I'm talking of. I'm going to draw carbon 4 as a dot. So this is my carbon 4. And then carbon 3 in the back, I'll draw that as a circle, much bigger than 4. Now, this isn't true. Carbon 3 in the back is the same size as 4, but we're going to draw it big like that so that we can see it, like, because it's hidden behind there, but we're going to distort things. We're going to draw it big. So just remember, carbon 3 in the back is bigger. So think of like carbon 3, baby's got back here. Big one, the back ones got baby's got back, got bigger. All right, so carbon 4 has a methyl 5 pointing down. Does that make sense? I'll emphasize it. I'll put CH3. This is carbon 5 right here. I'm imagining myself being in the plane of the iPad here, and I'm looking down. I see 3. I'm going to draw that as a dot. And then from my perspective, let me draw the rest of this person a little bit, though. Let me see if that's there. Then they'd have a forehead, right? And then they'd have a nose. And then some sweet lips. Here we go. There we go. And then like Adam's apple. Oh, yeah, there we go. What do you think? Give us some hair. Maybe we'll go nose ring. Oh, sweet nose ring right there. Yeah, there we go. Yeah. And maybe we'll do a face tattoo. We'll do something like this. I don't know what's going on here. We got like, bam, there we go. You know, let's put a hat on too, backwards. Yeah, indescript, some team symbol on there. Okay, so you see how Newman here, this Newman projection, carbon 4 is the dot in front, 3 is the circle, but carbon 4 for them, the methyl 5 is pointing down, huh? Methyl 5, they're gonna kiss it almost, right? It's right there, it's down for them. And then they also see 2 hydrogens coming up like that. And now there's hydrogens here. So over here on the left, from their perspective, do you think it's the yellow hydrogen or the red hydrogen over here? Is this the yellow or the red? It's the yellow. That's the yellow. Because like, if you think about it, their left hand is closer to us, like their left side. And so this is on the left. And then the red one would be on the right. There it is. Boom. Okay. And now carbon 3 is in the back. What do we have attached to carbon 3? We've got this isopropyl. That's what we call these, isopropyl, when there are 3 carbons, the propyl, and they're attached in the middle, isopropyl. We got isopropyl back here going up. See how it is going up relative to their perspective? This is going up. And then they have the 2 hydrogens are wedge dash. They're going down from their perspective. And you see how I'm attaching it to carbon 3, this outer circle. I'm not going into the middle because that's carbon 4. I need to be on carbon 3. Okay, so on the left here, what do I need? Blue or green hydrogen? It's the blue one. That's on their left. The blue and the yellow are both wedged on the same side, right? And then the green one goes here. And there we go. That's a Newman projection of this molecule viewing from 4 to 3. We did it. Okay, and then we're going to do more examples of this. But before I write out some more on the Jamboard, I'll show you what was made on Friday when I met with the honor students, the ones who could make it. And those who couldn't, I have the video of it being made. Let's see. Let's see here. Search it. Wait, no, Zach. Oh, I forgot about this one. Is this a good one? I think this is a good one too. Let me come back to that. Here it is, the one I wanted. Yep. So our honor students are going to be making up Newman projections for the following molecules. Oh no, this was just IR training. These are their assignments actually. These are their Newmans they're going to make up. And I did one. Oh, look at someone's making progress. I like it. Going with the theme there. Okay, so let's click through this. This is just a quick click through to see another example before I do some more. So the benefit of doing this, these Newman projections, is we're going to look at, after we get good at just looking down the bond, we're going to rotate the molecule and see when it rotates along the bond we're viewing. It can be higher in energy, then lower, then higher, then lower, and we can figure out how it's, like if it's lowest in energy here, that's what it looks like. So that's going to affect how it reacts. Yes, there is a Seinfeld reference because when you control the mail, you control information. So this is the mailman from Seinfeld. And Jerry Seinfeld, he hated that. They hated each other. So whenever Newman would come in, he'd go, Newman. So yeah, Newman. All right, so Newman projections are a method of looking down bonds, allow you to make easy predictions about energy differences of different conformations. So here I've got this bastard butane. And if I number it, you'll see it's got 4 carbons. And if I want to view from 3 to 2, which bond is going to be the dot? Is it carbon 3 or carbon 2? One's going to be a dot and one's going to be a circle. Which one's the dot, 3 or 2? Carbon 3 is the dot. That's right. Oh, and I drew it again with colors. So here's Newman. He's looking down that bond. Newman. So 3 will be the dot. Boom, there it is. And then how do I draw carbon 2, the one in the back? Not a dot, but a circle. And that's carbon 3. And then here's the circle, boom, in the back. And now carbon 4 is coming off of 3, right? How should I draw that on the Newman? Should it be pointing up, down, left, right? That's carbon 2. Actually, I'm working on carbon 2 in the back. And that's where the methyl on carbon 2 actually goes down, right? And then it has 2 hydrogens, yeah. So let's focus on 2. Does it make sense that 1 is pointing down? I originally asked about 3, but I forgot how I animated it. So yeah, 1 is in the back pointing down. Now this purple hydrogen on 2, should it be left or right? So where's my, yeah, the purple hydrogen needs to be on the left because it's on Newman's left. And then the yellow hydrogen is on the right. Okay, cool. And now carbon 3, I asked earlier, and I think most of you got it right. The methyl 4 should be pointing up. Yeah, that's carbon 4. And then down, the red and the blue are down at an angle. And the red one is it on the left or the right? On the left. The blue one's on the right. There we go. So now we got our Newman. And this particular conformation, this kind of conformation is called staggered. When we say staggered, what we mean is that this, say, if I reference this methyl, it's right in between the carbon, the back carbons, 2 hydrogens. It's right down the middle. But this bond right here, the bond between 2 and 3, it's a sigma bond and it can rotate, and it does. It rotates around. And as it rotates, the methyl can rotate and it can be eclipsing this like purple one. And then it can go and be staggered here, and then it can eclipse the other methyl and stagger. And then when it's doing this, it's at different energies. So let's go back to the Jamboard and do this. Oh, actually, I'll just show this one real quick. Let's see. Who made this one? One of my former honor students. I think I just saw their name, but I forgot it. So here's one. So this is the same bastard butane. See how we've got this methyl here and this methyl here? They're close to each other, but they're not eclipsing. This is staggered currently. And then if I take and I rotate, let me see, which one am I rotating here? I'm rotating the front carbon, this front carbon. There should be, I'd rather have a dot right here, but that's okay. He left the dot off. But so when I rotate around, now the methyl is going to be eclipsing the groups in the back. And when I draw them eclipsed, I don't draw them like perfectly eclipsing on top of each other because then you can't see it, but just a little bit off, this means they're eclipsed. So if I did a 60-degree rotation on the front, this would be eclipsed. Does it make sense that this eclipsing conformation is higher in energy than the staggered? Yes, the eclipsing is higher in energy because now there's electron-electron repulsion. They don't want to be right next to each other. But if I do another 20-degree rotation where I take this methyl and it pulls down to the staggered again, it's lower in energy. And you notice how, does that all come up at once? Yeah, it's kind of a lot of ones, but it's okay. So do you notice how now you're in a staggered, which is lower in energy than eclipsed, but also you have the two big groups, the big group in the back, the methyl, and the big group in the front, the methyl. They're completely opposite of each other. Whereas the hydrogens are smaller, right, than the methyl. So that's why this one is lower in energy than the original one. Does that make sense? Yeah. Oh, and then if I rotate again, put this methyl over here, eclipsing, higher in energy again. And it's the same as before because it's symmetric. Like you have a methyl hydrogen eclipse, methyl hydrogen eclipse, methyl hydrogen eclipse, methyl hydrogen eclipse. It's the same energy right across there. Yeah. Yep. And then if I do another rotation where I put the methyl right here, where it's staggered again, but it's closer to the other methyl. It's going to be the same energy at the start, but higher than when the methyls are all the way across from each other. And then finally, we do one more rotation. And when we do this last one, well, I think this is the last one. I think we'll do one more for this, but as we do this, this will give us our last unique thing. Now the two methyls, the two biggest groups are eclipsing each other. And when that happens, you're even higher in energy than the other eclipsed because you got two big methyls eclipsing. And then the last rotation puts you right at the beginning, same things we started. So it should be the same energy, right? Okay, so when we do these Newman projections, I'm going to ask you on the next exam for sure to do Newman projections, and I'll probably have you make a diagram like this. So it staggers lower in energy, then all the staggers are going to be lower in energy than all the eclipse. And then within the staggareds, you'll have some that are lower and some that are higher. And then same for eclipse. Within the eclipse, you have some higher and lower. I think that's it. Yeah, that was pretty good. View only. Yeah, nice. Okay, so let's see. Let's just do one more on the Jamboard, and then we'll call it for today. Okay, the last one we did, we viewed it from the upper right, huh? Let's view this one from the left. Let's go, I'll do a big terp butyl group and a methyl. Yeah, that'll be enough for now. Just imagine we're looking at it that way. That direction. I'll build the rest of the person. Let's go. Yeah, what I did. They got a sweet hairdo. Got the mullet. Business in the front, party in the rear. Yeah, there we go. This one looks a little squinty-eyed. Let's give him give him a nice ear, and then let's go with some sideburns. Let's give a little scruff, There we go. And maybe a little stash too. Cool. All right, so we're looking down this bond. I'm gonna give it one more. Let's give it a methyl there. Yeah, let's see what that looks like. And let's number this. Let's go 1, 2, 3, 4, 5. And we'll number this guy's name is 2,2,5 trimethyl pentane. Another pentane. Okay, I'm reviewing from carbon 3 to carbon 4. So here we go. I'll draw a dot for carbon 3, and then the terp butyl goes up from carbon 3. Do you agree? And then carbon 4 is big in the back. Baby's got back. And oh wait, I gotta draw off these other. Carbon 3 has 2 hydrogens. That's easy to tell. I didn't give them color this time. And then this is currently in a staggered conformation. So on carbon 4, I've got a 2 methyls and a hydrogen. That's carbon 4. So where's carbon 5? Is carbon 5 to the right, to the left, or down? Yeah, carbon 5 is down here. Okay, that one's an easy one. What about that? The methyl, I'll call it like A right here. Where's that wedged out A? Is that to the right or to the left? To the right, actually. A is right there. We're looking at it from the other side. Okay, so we have a hydrogen here. I'm going to simplify this one. Last time I wrote a little like CH3 on these. I put CH3. You can do that, but I'm just going to keep it like that because then we know that's a methyl by bond line structures. Okay, so now I got my initial structure. Let's do some rotations on it. Let's do a 60-degree rotation on this. And we can rotate the front or the back carbon. I tend to like to rotate the front more, but I'm going to let you choose. What are we going to do? Are we going to rotate the front or the back? Annalise, I can help you with the nomenclature later, but I want to just keep on this current thing. Okay, we're going to rotate the front. Okay, rotate the front 60 degrees. So that means I'm going to keep the back stationary. So I can draw that back carbon and its methyls just like that. Oh, and then our rotation. Do you want to rotate the front clockwise or counterclockwise? Okay, I'm hearing clockwise. Yep. This means that I'm going to go from this current staggered to an eclipsed. Eclipse, C-L-I-P. Ah, so bad. E-C-L-I-P-S-E-D. Eclipsed. And the way we're going to draw the eclipse is we're going to be careful. We're going to draw the things like right next to it, but not perfectly overlapping like that. So it's not a true eclipse because true eclipse, you couldn't see the back one. We're kind of skewing it a little bit. And so I did show that the tert-butyl went 60 degrees to be eclipsed here. And so then this hydrogen went to here and the other hydrogen went to there. There's my eclipse. So out of the two of these, which one's lower in energy, the staggered or eclipsed? The staggered's lower in energy. Things are further apart. Okay, let's do one more and then we'll take a break. We'll do another 60 degrees, same thing. The back carbon is rotating or staying still, sorry. So the back carbon still has this hydrogen, the methyl, and the methyl. And the front carbon now is going to go back to staggered. Staggered. E-R-E-D. Okay, so we're back to staggered, got lower energy, but let's compare these two. Are these two the same energy? Which one of those? Are they the same energy or is one lower? They're not the same energy. I'll help you with understanding this. This is how I like to think of it. I'll just draw the back carbon. So this back carbon has a methyl here, a methyl down here, and a hydrogen here. And it's kind of got 3 quadrants, or no, not quadrants means 4, right? 4 areas. This is 3 tridents. Is that what you'd say? I don't know. But it's got area 1, area 2, and area 3. It's got 3 areas that you can be staggered in. And they have different steric hindrance. So I'd say, which area has the most steric hindrance? Area 1, 2, or 3? Your question is, your answer to your question, Ryan, is yes. So area 2, most steric hindrance. Oh, have I defined steric hindrance? Electron repulsion. Repulsion. Most electron repulsion. That steric hindrance describes like that. When atoms are closer together, they hinder each other. And the steric refers to size, like their size hindrance. Okay, so the most steric hindrance there, and then areas 1 and 3 have the same steric hindrance. Okay, so that means in this conformation, in the bottom right, I've got my large, what's called turb-butyl group in the most crowded area. And then on this one, I've got it in a much less crowded area. So this one's lower in energy. And that one. All right, so then we'll pause there. And the next lecture, I can take this example or a different one, and I'll make a full energy versus rotation diagram like this.